The Subcommittee on Space will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. And welcome to today's hearing titled Planetary Flagship Missions, Mars Rover 2020 and Europa Clipper. I now recognize myself for 5 minutes for an opening statement. NASA's planetary science flagships are the crown jewels of our robotic exploration of the solar system. Viking, Voyager, Galileo, Cassini, Chandra, and Mars Science Laboratory are programs that have inspired generations of Americans. One need only visit a local elementary school to see the wonder in children's eyes as they learn about the great discoveries of these flagship missions. Mars Rover 2020 and the Europa Clipper will be no less amazing. Upholding such a legacy is not easy. From its original recommendation by the National Academies, through formulation and development, and ultimately launch and mission operations, there is much work to be done to ensure mission success and that the taxpayers' money is being appropriately spent and that the national interest is being met. Today's hearing serves an important oversight purpose. Our witnesses will provide important testimony on the Mars Rover 2020 and the Europa Clipper, both from a programmatic and science perspective. The hearing will also provide an opportunity for committee members to learn about the science that these missions will conduct and how it will benefit our nation. I have full faith that NASA and its hard-working men and women will carry out its planetary science flagship missions successfully. That said, NASA is entering the most critical stage of the Mars Rover 2020 development and is undertaking the development of the Europa Clipper and possibly a Europa lander at the same time. For Mars Rover 2020, the NASA Inspector General reported concerns regarding an overly optimistic schedule for Mars Rover 2020 based largely on technology development challenges. I look forward to hearing from Dr. Green about these issues and how NASA is addressing them. A fundamental oversight question that needs to be addressed is how developing and operating these flagship missions at the same time, including a possible lander, will affect the Planetary Science Division and broader Science Mission Directorate portfolio. NASA must remain vigilant to protect against potential cost growth or mission creep that could impact other activities. The Consolidated Appropriations Act of 2017 funded and requires a Europa lander mission to complement the Clipper. The Act directed NASA to launch the Clipper in 2022 and a lander in 2024. In fiscal year 18 President's budget, his request does not include funding for a Europa lander. NASA says that because the Planetary Science Division already supports two other large strategic missions, Mars Rover 2020 and Europa Clipper, it cannot accommodate a Europa lander without significant impacts to other programs. And while a Europa lander is not included in the fiscal year 18 budget request from the administration, it has become an established concept for the future. NASA's Europa lander science definition team conducted a study of the topic in 2016 to evaluate landing on Europa and assess the science value and engineering design of a future lander mission. Most recently, NASA released a community announcement to ask scientists what instruments would befit a Europa lander, and NASA continues to work on lander design concepts. I strongly support NASA and its efforts with the Mars Rover 2020 and Europa Clipper. I also believe there is great value in exploring the possibility of a Europa lander. However, it is critical that as Congress and NASA move forward, we do our due diligence to assure not only flagship mission success, but also the success of the entire planetary science portfolio. I'd like to highlight the importance of sufficient research and analysis funding so that scientists can actually study the data derived from these missions. I want to thank the witnesses for being here today, and I look forward to your testimonies. And now I recognize the ranking member, the gentleman from California, for an opening statement. Mr. Barrow.
Thank you, Mr. Chairman. And I had to look back there. I see my old friend and our former colleague, Congressman Matt Salmon, in the audience. So, yeah, we miss you, Matt. So, thanks for being here.
I just saw him too.
Thank you for holding this hearing. Planetary Flagship missions, Mars Rover 2020 and the Europa Clipper. I think for both of us, we've talked about this, and for many of us of a generation that grew up in the space race, just the imagination, thinking about whether it was going to the moon or beyond, these the Apollo missions to Skylab, to Apollo-Soyuz, to the space shuttle programs, captured our imagination. And to a new generation of our kids and grandkids, they continue to capture our imagination of going beyond. And we live in a time where we've sent spacecraft to explore the moon, all 8 planets, Pluto, several asteroids, and comets. And just last week, the NASA Juno spacecraft provided us with an amazing view of Jupiter's mysterious Great Red Spot. So, these missions are incredibly important because it allows us to know that we're part of something bigger. And now we've got Voyager 1 that is traveling through interstellar space. The reach of scientific exploration is truly inspiring. And to maximize the scientific return on investment for planetary exploration, NASA develops both large and small missions to visit a range of destinations throughout our solar system. We're here to talk about large flagship missions like Mars 2020 and Europa Clipper missions because they play an important role in using complex instruments to help us understand the challenge of exploring hard-to-reach locations. But we spend less time talking about the smaller missions, like the Psyche mission that's represented on our panel. These are launched much more frequently in response to new discoveries. These missions also provide opportunities for students to engage in mission design, development, and operations. So the mixture of both the large planetary missions but also the small is an intentional mix, and it provides significant value and has through the history of NASA's planetary science program. We also know that NASA's planetary missions have greatly advanced our understanding of the solar system and its potential to harbor life beyond Earth. Now, imagine if we were to identify life beyond Earth. That would be disruptive for all of humanity in a way of answering that seminal question, are we alone? And life may not be in the form of human life. It may be microbiotic life, et cetera. But even that discovery would be dramatic and change how we viewed ourselves in the context of our universe. So, I look forward to learning more about the role of large and small planetary missions and the importance of supporting this balance of mission size. And, I want to acknowledge the panel here. I also want to acknowledge the long-term commitments that we make as a body to fund this discovery, and it's incredibly important to us. So with that, I'll yield back.
Thank you, Mr. Barrow. I now recognize the ranking member of the full committee for a statement, Ms. Johnson.
Thank you very much, Mr. Chairman. Before I get into my formal statement, I just want to take a moment to say that this Friday marks 48 years of Apollo 11 moon landing. And as we look forward to inspiring our younger generation, whom I know is many are sitting right out there, for the exciting future missions to Mars, Europa, and the asteroids, just remember that just 48 years ago this Friday, we had a previous generation of young people. America has an impressive legacy of accomplishment in both robotic and human space exploration. And I hope that we can continue to build on it. I hope that your minds will be just as inspired for our future as we have seen for our past. Now for my formal statement. Let me welcome all of our witnesses. I look forward to your testimony. Mr. Chairman, I thank you for holding this hearing on planetary flagship missions. Through our investigations in NASA's planetary science program, NASA has been able to explore every planet in the solar system, as well as Pluto. continuously operate missions to Mars for the past 2 decades and discover an expanding realm of potentially habitable bodies both within and beyond the solar system. With each discovery, NASA is advancing knowledge, pushing technological boundaries, and inspiring future generations to pursue science and technology education and careers. That is why I have often referred to NASA's science program as one of America's crown jewels. And we will hear this morning even more exciting planetary science missions lie ahead. As I speak, NASA is developing 2 planetary flash missions. The Mars 2020 rover will access the habitability of Mars and look for signs of past life. In addition, Europa Clipper mission will investigate the ice shell of Jupiter's moon, Europa, and its underlying ocean, helping scientists to assess whether it can support life. These, like other flagships, are very challenging missions. Mars 2020 will drill, collect, and cache samples of Martian rocks and soils, and Europa Clipper must withstand the intense radiation environment of Jupiter. Fortunately, NASA has decades of experience with flagship missions to draw on. With that in mind, I hope our witnesses can discuss the lessons learned from previous flagships and how we are using that knowledge in developing Mars 2020 and Europa Clipper missions. Mr. Chairman, a discussion of flagship missions would be incomplete without mentioning the importance and the balance in mission sizes, a critical element of robust portfolio for both the National Academies and NASA Authorization Acts have repeatedly emphasized. To that end, I am pleased that this morning's discussion will also include smaller Discovery class missions and their role in maintaining a productive and balanced planetary science program. Looking ahead, opportunities for new and exciting planetary science missions abound. Maintaining balance will take discipline among NASA, the scientific community, and Congress. Before I close, I want to take a moment to thank the talented, dedicated, and committed workforce of NASA and its university, industry, and international partners. Our nation's inspiring achievements in planetary science would not be possible without all of you. I thank you, Mr. Chairman, and yield back.
Thank you, Ms. Johnson. I now recognize our chairman of our full committee, Mr. Smith from Texas.
Thank you, Mr. Chairman. The exploration of our solar system captures Americans' interest, inspires us to pursue extraordinary goals, and keeps us on the forefront of scientific achievement. Planetary missions teach us about how our solar system works and provide clues about how it was formed. They discover the locations of minerals and potential water sources on asteroids, comets, moons, and planets that could be used in future human missions, or in the case of minerals, extracted for use here on Earth. Planetary science also helps address a fundamental question of science. Is there life elsewhere in the universe? Within our own solar system, scientists have found strong evidence that other planetary systems could in fact host life. Europa, one of Jupiter's many moons, may have the necessary ingredients for life: water and energy. Its ocean lies beneath an icy surface and may be 2 times the volume of all Earth's oceans. Tidal forces drive active geological processes within Europa's ocean interior and provide energy. Scientists see similar activity in hydrothermal vents on Earth's ocean floor. The Europa Clipper mission, a flagship mission recommended by the National Academy of Sciences, will be an important mission to address the scientific question of whether there is life elsewhere in the universe. It will advance our understanding of planetary science as it explores the characteristics of Europa's oceans, ice surface, and other geological activity. Congress directed NASA to work on a Europa lander to complement the Europa Clipper. NASA's Europa Lander Science Definition Team conducted a study on the topic in 2016. The study found that the mission could analyze the biological potential of Europa's ocean by directly examining both Europa's surface and subsurface. This is a very exciting concept that warrants NASA's continued efforts. Closer to Earth, Mars Rover 2020 will also study the habitability of Mars. It builds upon the discoveries from the Mars Curiosity rover and the two Mars exploration rovers, Spirit and Opportunity. The mission not only seeks signs of habitable conditions of Mars past, but also searches for signs of past microbial life itself. It will also test new technology that could benefit future robotic and human exploration of Mars. One of its instruments, MOXIE, will test a method of producing oxygen from the Martian atmosphere. Oxygen production on Mars will be critical for future human missions. And I appreciate NASA's planetary science exploration efforts and the Trump administration's support of American leadership in space. Other than national security agencies, NASA received the most favorable budget request from the Trump administration. As a result, we can look forward to NASA undertaking a bold and ambitious agenda. I thank our witnesses, look forward to their testimony, and I'll yield back, Mr. Chairman.
Thank you, Mr. Chairman. Now let me introduce our witnesses. We have a distinguished panel this morning. Our first witness today is Dr. Jim Green, the Director of the Planetary Science Division of the Science Mission Directorate at NASA. Welcome. Dr. Green has served as the Chief of the Space Science Data Operations Office at Goddard Space Center, as well as the co-investigator and Deputy Project Scientist on the IMAGE mission. He received his PhD in space physics from the University of Iowa. Welcome. Our second witness today is Dr. Ken Farley, the Mars Rover 2020 project scientist. He is also a professor of geochemistry at the California Institute of Technology. He received his Bachelor of Science in Chemistry from Yale and a doctorate in Earth Science from the Scripps Institution of Oceanography from the University of California in San Diego. Welcome. Our third witness today is Dr. Robert Pappalardo, the Europa Clipper project scientist at JPL at the California Institute of Technology. Dr. Pappalardo received his Bachelor of Arts in Geological Sciences from Cornell University, as well as a PhD in Geology from Arizona State University. Maybe that's why we see Representative Matt Salmon back there. Dr. Linda T. Elkins-Tanton, our fourth witness today, Director and Foundation Professor at the School of Earth and Space Exploration at Arizona State University. She is also the Principal Investigator for the NASA Psyche mission. She received her Bachelor's of Science and her Master's of Science, as well as her PhD from MIT. Our fifth witness today is Dr. William B. McKinnon. He is co-chair of the National Academy of Sciences Committee on Astrobiology and Planetary Science. He is also a professor of Earth and Planetary Sciences at Washington University in St. Louis. He received his Bachelor of Science degree in Earth and Planetary Sciences from MIT and his PhD in Planetary Science and Geophysics from Caltech. I would like to now recognize Dr. Green for 5 minutes to present his testimony.
Chairman Babin and the members of the committee, thank you so very much for giving us the opportunity to come and talk about certainly my favorite subject, planetary science. In my opening statement, I'd like to explain how missions like Mars 2020 and the Europa Clipper fit into an overall planetary exploration portfolio. In my first chart, as you see, this is an overview of the current planetary missions. They're in a variety of formulation, implementation, and currently operating missions that we have. This is a tremendously exciting time in planetary science. All our operating missions are making revolutionary discoveries, and all are rewriting the textbooks. For instance, just 2 years ago, we had a fabulous flyby of the New Horizons spacecraft through the Pluto system. With that mission, the United States becomes the first and only nation to reach every major body in the solar system from Mercury to Pluto. Dr. Bill McKinnon on the panel is a New Horizons co-investigator. Today, NASA has numerous missions exploring and operating through the solar system, such as the Lunar Reconnaissance Orbiter, which is bringing us back to the moon and making exciting discoveries. The indomitable Mars Curiosity and Opportunity rovers, along with our orbiters at Mars, continue to make almost daily new discoveries about the red planet. For example, from our MAVEN mission, it has revealed that solar wind interactions with the upper atmosphere of Mars over time has literally stripped away most of that atmosphere, transforming Mars from what we believe was once a planet that could have supported life in its distant past to now a frigid, arid world. Adding to our Mars missions, InSight lander will be launched in May 2018 and land in November 2018. InSight is designed to study the interior of Mars, along with understanding its present-day level of global seismic activity. In 2020, a new Mars rover will be launched, carrying 7 state-of-the-art instruments to conduct advanced geological research and search for signs of ancient Mars life. For the very first time, we will create high-grade rock core samples for potential return to Earth for further analysis. I look forward to Dr. Farley's testimony, which will provide additional information on that mission. Between Mars and Jupiter is a major asteroid belt, where NASA's Dawn mission is currently studying the dwarf planet series and finding evidence of past cryovolcanism. This year, NASA selected 2 discovery missions, Lucy and Psyche, which will, respectively, visit 6 Jupiter mysterious Trojan asteroids and study a unique metal asteroid that may actually be an exposed planetary core called Psyche. Dr. Lindy Elkins-Tanton is here today to tell you much more about the Psyche mission. NASA's robotic rendezvous and sample return mission that visits the Bennu asteroid is called OSIRIS-REx. It will get a gravity assist by Earth in September, and it will reach that potentially hazardous asteroid in August of next year. Examinations of objects like Bennu will allow our scientists to investigate how planets formed and how materials like water and organics actually were delivered in early impacts, in addition to looking at the effects of potential planetary defense. In our outer solar system, Jupiter's mission Juno, which got into polar orbit, our very first time in polar orbit at Jupiter last July. Since then, Juno has been observing the cloud tops and into the interior of the planet, finding in the northern and southern polar regions that that planet is maintaining huge, nearly Earth-sized cyclones. After 13 years of orbiting Saturn, our Cassini spacecraft is making a daring dive between the planet's atmosphere and the first ring. And it will lead to plunging that spacecraft into Saturn on September 15 as it runs out of fuel. Cassini has given us a powerful insight into the planet's internal structure, atmosphere, and rings, in addition to unbelievable views of Titan and Enceladus. And if I may go on and summarize. Finally, NASA recognizes there is still much to learn. With your support, we will continue to tackle solar system exploration goals identified as top priorities by the scientific community and delineated in the National Academy's Planetary Decadal. Again, thank you so much for the opportunity to testify today, and I look forward to responding to your questions.
Thank you, Dr. Green. And now I recognize Dr. Farley for 5 minutes to present your testimony.
Thank you for the opportunity to testify today on the Mars 2020 mission. Mars 2020 will seek evidence of past life in a fossil Earth-like environment that existed in the first billion years after the dawn of the solar system. This flagship mission will engage many hundreds of scientists and the American public in a very challenging journey through one of the most intriguing landscapes in the solar system and some of the most profound scientific questions of our time. Today, Mars is too cold, too dry, and too exposed to harmful radiation to plausibly nurture life on its surface. However, more than 2 decades of sustained and strategic NASA-led exploration have shown that the red planet was once very different. Imagery from the Mars Odyssey and Mars Reconnaissance orbiters reveals that prior to about 3.6 billion years ago, Mars had rivers, lakes, and possibly a vast northern ocean. Sophisticated analyses made on the planet's surface, most notably by the Spirit and Curiosity rovers, have richly documented ancient environments with all conditions believed necessary to sustain life. In that same early time period, conditions here on Earth were broadly similar, and life had already originated, evolved, and spread across the surface. However, unlike Earth, with its active erosion and plate tectonics, the geologic record of ancient Mars is exquisitely preserved for study, allowing us to seek answers to grand questions, including how early climate and habitability evolve on rocky planets, the nature of prebiotic environments that might ultimately spawn life, and whether life is unique to Earth. Seeking the signs of life in an ancient habitable environment is the central goal of Mars 2020. Thanks to a wealth of images from the Mars Reconnaissance Orbiter, the science community has narrowed the possible Mars 2020 landing sites down to 3 very different settings that on Earth are both habitable and inhabited: an ancient river and lake system, a fossil hot spring similar to those at Yellowstone National Park, and a setting where warm water once circulated through shallow subsurface rocks. Once on Mars, the rover will use its onboard instruments to investigate the local geology, to characterize the habitable environments the rover traverses, and to look for evidence of ancient life. Using Earth as a guide, we expect that any Martian life existing at that time was primitive, consisting only of microbes. Truly definitive discovery of microbial biosignatures by instruments on board the rover is unlikely and can best be undertaken using the full arsenal of terrestrial laboratories. For this reason, the Mars 2020 rover will prepare a complete suite of samples for possible return to Earth by a future mission. Mars 2020 starts with the designs of the remarkably successful Mars Science Laboratory, MSL, and the Curiosity rover. To this platform, a suite of very capable new science instruments is being added to explore the structure, chemistry, and mineralogy of the surface, all the way from the regional scale down to the microscopic. In addition, the mission is developing advanced new capabilities for landing in rugged terrain, for autonomous navigation and science observation, and for robotic coring and caching of samples. These are critical steps towards unleashing the full capabilities of a robotic solar system investigation. The mission will also test new technologies beneficial to future human Mars exploration, most notably a device to demonstrate conversion of carbon dioxide in the Martian atmosphere into oxygen for use as a component of rocket propellant. The mission is currently in the implementation phase, Phase C, with a substantial amount of hardware already completed. Launch will occur in the summer of 2020, with arrival on Mars on February 18, 2021. The rover will be landed using the spectacular Sky Crane system pioneered by MSL and will explore the Martian surface for at least 2 years. In that period, the rover will core and cache at least 20 rock samples, each about the size and shape of a piece of chalkboard chalk. These will be thoroughly documented and placed on the surface, accessible to retrieval by a future mission or even by human explorers. By collecting and caching a diverse suite of high science value rock samples, Mars 2020 fulfills the highest priority objectives of the Mars and planetary science communities as described in the most recent Planetary Science Decadal Survey. Mars 2020 will investigate a planet known with detail sufficient to compellingly address, for the first time, well-posed and profound scientific questions that would forever elude answers from Earthbound study. Going well beyond observations on the Martian surface, return of the cache to terrestrial laboratories would provide future generations of scientists across many disciplines access to samples that would transform our understanding of Mars, the solar system, and life. There's still an enormous amount to learn about Mars, and the deeper we penetrate, the richer the scientific tapestry becomes. Mars 2020 makes the next big step in this decades-long journey and provides new focus and foundation for human exploration of Mars. It's an honor and a privilege for me to play a part in such a grand and ambitious undertaking, and I look forward to your questions.
Thank you, Dr. Farley. Now recognize Dr. Pappalardo for 5 minutes to present your testimony.
Chairman Smith, Chairman Babin, Ranking Member Vera, and other members of the committee, I'm delighted to appear before you to describe recent progress in NASA's Europa Clipper mission. The ice-covered world Europa, a moon of Jupiter similar in size to Earth's moon, shows a landscape of cracks, ridges, and jumbled chaotic terrains indicative of a tumultuous past. The Galileo spacecraft, which orbited Jupiter beginning in the late 1990s, provided images, compositional information, and gravity and magnetic data that point to a remarkable conclusion. Europa likely has a global ocean of liquid water beneath its icy carapace, maintained by tidal flexing and heating. From what we know of the tenacity of life, Europa could be one of the best places in the solar system to search for life beyond Earth. For these reasons, future detailed investigation of Europa is one of the top priorities for planetary exploration, as expressed in the National Research Council's 2011 Planetary Science Decadal Survey. The Europa Clipper mission responds directly to the Decadal Survey and its top-level goal, explore Europa to investigate its habitability, and in its science objectives to understand Europa's ice shell and ocean, composition, geology, and recent and current activity. The last of these categories includes the possibility that Europa may have active plumes that spew water vapor into space, and which could directly reveal Europa's internal composition and suitability for life. This tantalizing evidence for plumes is provided by the Hubble Space Telescope, searching at the extreme of its detection limits. In the tradition of the 19th century trading ships for which this mission was recently named, the Europa Clipper will sail past the Jovian moon at a rapid clip, as frequently as every 2 weeks, providing many opportunities to investigate Europa from as close as 16 miles above the surface. During each flyby, the spacecraft will spend just a short time within this challenging radiation environment near Europa. The prime mission plan includes 40 to 45 flybys of Europa from Jupiter orbit, during which the spacecraft will interrogate the moon in unprecedented detail. This will include imaging to understand its geological history, compositional analyses, including direct sampling of materials knocked off of the surface, ice-penetrating radar to examine the 3D structure of its icy shell, and gravity, magnetic, and plasma measurements to understand its hidden interior and interactions with the Jupiter environment. The mission can also lay the foundation for future exploration of Europa, providing critical global context and scouting potential landing sites for a potential future landed mission. As its project scientist, I represent the science and scientific integrity of the Europa Clipper mission, ensuring it will address the top-level goal and objectives. I first testified before this committee 2 years ago, just after NASA had competitively selected 9 science instruments for the mission and had given the green light to begin Phase A, known as mission formulation. In February of this year, NASA completed its second major milestone review. So today we're in Phase B, refining details of how the instruments will achieve the mission science and developing preliminary yet detailed design plans for the spacecraft and its subsystems, including the science instruments. Progress on the instrument suite has been outstanding. Instrument concepts have been reviewed, designs have been matured, subsystem vendors are being selected, prototype parts are being built, detectors are being tested, and additional tests are being conducted to ensure robustness against the harsh radiation environment in Europa's vicinity. Beginning this fall and into next spring, each spacecraft subsystem and each instrument will undergo a preliminary design review to assure that the defined science can be achieved by the instruments and spacecraft in combination. These Phase B reviews are in preparation for the mission to proceed to Phase C around October 2018. It's also at that key decision point that NASA would make a final commitment as to launch readiness date and baseline mission cost. Then during Phase C, flight hardware would be built. The members of the mission science team are working cooperatively to define the synergistic science, which I see as this mission's hallmark. No one instrument can definitively affirm the ocean's existence or tell us convincingly of Europa's composition. Instead, each instrument technique provides a piece of the puzzle, and from the combined science data, Europa scientists will mature a complete picture of how Europa works as a complex system, from its submerged rocky core to its ocean to the capping ice shell and surface to its thin atmosphere and the surrounding environment of Jovian space. The clipper ships of the late 19th century were an expression of speed and grace in the golden age of sail. We're now in a golden age of solar system discovery, and the Europa Clipper mission will return to us untold scientific riches. Thank you, and I look forward to your questions.
Thank you, Dr. Pappalardo. Now recognize Dr. Elkins-Tanton for 5 minutes to present her testimony.
Chairman Babin, Chairman Smith, Ranking Member Bera, and the members of the committee, thank you so much for the opportunity to speak today. Today I'll be testifying in my personal capacity. Any discussion of NASA's planetary science program would be incomplete without also talking about the balance between flagships and smaller planetary missions. And so today I'm going to talk about 3 things. I'm going to talk about the newly selected Psyche mission, I'm going to talk about portfolio balance, and I'm going to talk about our inevitable space future. I am the principal investigator of the Psyche mission, which in January was selected as the 14th in NASA's Discovery program. The spacecraft is scheduled to launch in August of 2022 to rendezvous with the asteroid Psyche in January of 2026 and to orbit Psyche for 22 months. Psyche is a metal world with a diameter about the same as the width of Massachusetts and with a surface area larger than the area of Texas. Humankind has explored rocky worlds, and we have explored icy worlds, and we have explored worlds covered with gas, but we have never before explored a metal world. This is a first. We think that Psyche is the core of a small, early formed planet that was bombarded in the early solar system and had its rocky exterior knocked off so that only its metal core remains showing today. Computer models of planetary formation indicate that this is rare. And indeed, Psyche is the only large, round metal object in our solar system. So it's not just unique, it's improbable. The science we hope to achieve in the mission is first to determine whether indeed Psyche is a core or if it is some previously undiscovered kind of material. We'll be comparing what we learn at Psyche to models of the Earth's core to better understand that unreachable part of our own planet. And for the first time, we'll be investigating the morphology of a metal body. What do craters into metal look like? Could Psyche have glittering cliffs of metal and green pyroxene crystals? We don't know yet. No one knows yet. At Psyche, we will also take the first steps toward our space resource future because we're pretty confident that Psyche almost entirely consists of iron, nickel, copper, and a variety of trace metals. Now, I strongly support the Planetary Decadal Survey's conclusion about the necessity for having a balanced mission portfolio, combining small and mid-sized missions on a regular tempo with flagships. Tempo is critical. Tempo maintains our workforce, and it also saves our institutional memory. But each size of mission comes with its own challenges and its own advantages. For smaller missions like Psyche, usually keeping costs down and keeping risk down means that we're going to use trusted high heritage components, whereas flagship missions give us the opportunity for innovation and new technology development, and we need both of those things. We need our trusted technology of today, and we need new technology for the future. Flagship missions can also engage a broader swath of the community through competed calls for instruments. These calls can bring new groups into missions that would otherwise not be involved, but then the project scientist has the challenge of organizing and uniting otherwise disconnected sub-teams. It's an interesting challenge. In fact, all lead scientists have to build, inspire, and lead large interdisciplinary teams, and normally engineers and scientists are not taught these skills. So we are trying to change that at ASU now. Exploration is a human imperative. It is stamped on our DNA, and space is the future of exploration for humankind. Every time we do this most extreme of technological miracles and we send a rocket off of our Earth to make discoveries in space, we encourage people all around the world to make a bolder step in their own lives and in their own communities. So space exploration is therefore an opportunity for us to create a better educated, more united society. At ASU, I'm also co-chair with President Michael Crow of our new Interplanetary Initiative. In this initiative, we're bringing together not just the technological, but the educational and the social aspects that we need for our space future. And indeed, education is the single most critical thing for humanity's future. Both at ASU and at our startup, Beagle Learning, we are working on next generation learning. We need to produce a critical mass of people who are attracted to the unknown, who are learning how to ask better questions, who are willing to pursue answers through partial solutions, and who know how to build teams and to lead. All this ideation is initiated by the vision and the process of NASA. And in fact, space exploration will bring us to a better future here on Earth, as well as eventually on the moon and Mars and beyond. Thank you very much.
Thank you, Dr. Elkins-Tanton. Now I'd like to recognize Dr. McKinnon for 5 minutes.
Good morning, Mr. Chairman, members of the committee. So I'm here today because I'm a co-chair of the Committee on Astrobiology and Planetary Sciences, or CAPS for the National Academies. But I wish to say that my testimony today is my own and is not an official report from CAPS or the academies. Nevertheless, I hope you find my remarks useful. So I'd like to focus on the Planetary Science Decadal Survey and its relation to Flagship and other planetary missions. Obviously, decadal surveys are carried out about every 10 years for various space science disciplines, and the committees and the panels that carry out the decadal are drawn from the broad community associated with the discipline in question. Decadal survey recommendations to the government play a critical role in defining our country's agenda in a given science area for 10 years or even longer. Now, the Planetary Science Decadal Survey was tasked in particular, among many things, to create a prioritized list of flight investigations because missions lie at the heart of planetary exploration. Such a prioritization is based first and foremost on science, especially science per dollar, but also on programmatic balance among mission targets and balance among mission types, small, medium, and large. And indeed, a balanced mix of discovery, new frontiers, and flagship missions enable both a steady stream of new discoveries and the capability to address larger challenges such as sample return missions or outer solar system exploration. Prioritization also considers technological readiness, the availability of trajectory opportunities, understanding of cost and technological risk, and the fiscal climate. Anyway, these prioritizations take in the sense that decadal surveys succeed because the consensus they represent is compelling. Now, in terms of science, increasingly central to NASA's exploration of the solar system is the emerging science of astrobiology, prominent examples being the scientific program of the Curiosity Mars rover, the Mars 2020 rover, the development of the Europa Clipper mission, and the planning for the potential future landing on the surface of Europa, and the inclusion of ocean worlds in the recent New Frontiers call. Indeed, in the most recent planetary decadal survey, astrobiology was a driving scientific rationale for the two top mission recommendations, now being implemented as Mars 2020 and Europa Clipper. Now, my personal assessment, and as the CAPS leadership has previously reported to the Space Studies Board, is that NASA's Planetary Science Division is doing well, and the decadal survey's priorities and recommendations are being pursued. Mars 2020 and Europa Clipper in particular are, I believe, responsive to the decadal survey in science and cost. Now, regarding NASA's plans to explore Europa, CAPS, as well as the ongoing Academy's planetary midterm review, will continue to consider the impacts of the evolution of this program. Presently, NASA has been directed to add a lander to the Europa exploration program. The development of any large mission like that is, of course, a programmatic challenge and can have unwelcome or worse effects on a broader cost-contained program. But this challenge must be balanced against the scientific opportunity afforded by the promise of addressing one of the greatest of scientific questions: is there extant life beyond Earth? As I said, these are all issues I expect CAPS will continue to consider and will also be surely considered by the next decadal as well. So to finish up, Mr. Chairman, as a second grader, I watched the liftoff of John Glenn in Friendship 7 in our auditorium. And as a teenager at home, I watched Neil Armstrong walk on the moon. Over these past 60 years, I have seen NASA's exploration of the solar system from Mercury out to Pluto and beyond revolutionize our conception of ourselves and our planet. But I believe, given our ongoing discoveries and characterization of planets around other stars, thousands of them we know about now, and the very real possibility of detecting extant life in our solar system, that we are approaching an even greater revolution, a true paradigm shift in our understanding of our place and our destiny in the universe. Thank you very much.
Thank you, Dr. McKinnon, of all fascinating testimonies. Really appreciate it. The chair now recognizes himself for 5 minutes. Dr. Green, In the near future, NASA's Planetary Science Division may be running 3 flagship missions at the same time. The Mars Rover for launch in 2020, the Europa Clipper for launch in 2022, and potentially a Europa lander for launch in the 2024 timeframe. I greatly support this investment and NASA's renewed focus on deep space exploration. At the same time, from an acquisition perspective, this is a great deal of work. What is NASA doing to address the risks of cost and schedule slips associated with this cadence of flagship missions?
Planetary science, I think, has tackled a number of those topics and is doing quite well because we've started to implement a couple very important and new procedures. Typically, strategic missions, and NASA's done it in the past based on a science rationale that's almost at any cost. And in planetary science, we have begun the process, in particular with Mars 2020, to have a cost-constrained environment. As was recognized in the planetary decadal, both the Mars Cacher and the Europa Clipper were unaffordable, and we took on a process early in this decade to begin to determine what science we can do at that reasonable cost. We are leveraging on Mars 2020 the architecture for Curiosity. We've done a lot of work on the planning of the Europa Clipper, where we're looking at D-scope options. And so some of these processes are incredibly important for us to follow through on.
Okay, thank you very much. And now the next question to Dr. McKinnon. To what extent do the Mars Rover 2020 and Europa Clipper missions align with the decadal survey recommendations?
Well, the original survey considered 2 flagship class missions, Mars Astrobiology Explorer Cacher, and a Europa Jupiter orbiter mission, a mission to orbit Europa itself. And in both cases, the decadal survey concluded, based on a very detailed cost and technical evaluation, that these missions were probably too expensive to be carried out in the decade in question. And so basically they were said, these were our priority missions, but they needed to be de-scoped. They needed to be reduced in cost and perhaps reduced and certainly reduced in risk. And in both cases, I think they've done that. As an example, the Europa mission doesn't orbit Europa anymore, but it orbits Jupiter, but repeatedly passes by Europa dozens of times and basically recovers all of the science. And in fact, in my own view, actually does an even better job because it avoids so much of the radiation that's near Jupiter, and it allows, in its long looping orbits around Jupiter that Dr. Pappalardo can tell you about, it can radio back all the data that it collects every time. So, and it does it within a very reasonable cost cap.
Thank you very much. Now, I also would like to ask Dr. Farley and Dr. Pappalardo, the exploration of Mars and Europa are inspiring and truly amazing. As project scientists for Mars Rover 2020 and the Europa Clipper, can you share with us what excites you about these exploration efforts? And what are the greatest scientific discoveries that you're hoping to achieve?
Well, I think the most exciting thing about Mars is that, as I mentioned in my testimony, the surface of Mars carries a rock record from a time period which is completely obliterated on Earth. There is no substantial rock record that is older than about 3.6 billion years on Earth. But those rocks are present on the surface of Mars, and they will tell us a lot both about the way rocky planets evolve and also about things like habitable environments. And for me, the linking this to the life question, I think the really exciting thing is we will potentially be looking at an environment that was capable of having life originate. And that's, of course, one of the great questions. It's a great scientific question that is extremely difficult to treat as a science question because there's no evidence, no substantial evidence to compare it against. By going to Mars, we may actually be able to find environments like that and learn something really profound about the way life works.
Thank you very much. And Dr. Pappalardo.
For Europa, we want to understand, is this really a habitable environment? Europa's ocean, lakes within the ice shell. And we think we know how Europa works, but planetary scientists are always surprised when we actually go there with new instruments to test hypotheses. So we're going to both test hypotheses and explore and expect to be surprised. What I would love to see is some sort of oasis, that is a place where there's liquid water near the surface, there's evidence of heat coming out, there are organics at the surface, somewhere where we'd want to follow up with future exploration.
Fascinating. Thank you. My time is up, so I'd now like to recognize the gentleman from California, Dr. Berra.
Thank you, Mr. Chairman. Dr. Elkins-Tanton, and I think each of you in your opening statements alluded to the fact that exploration is part of our DNA. You know, this natural curiosity, this desire for discovery, and the universe is, you know, unlimited in its possibilities of what we can learn. That brings us back down to Congress, where we have to operate in the confines of limits. Each of you has talked about the decadal survey and alluded to a bit of the roadmap for some of our bigger missions, and laying out some of the parameters for some of the medium-sized missions. But Dr. Elkins-Tanton, as you talked about the Psyche mission and alluded to the importance of, you know, some of our smaller missions, how those, you know, what we discover, you know, they're able to be launched at a lower cost, et cetera. You know, there is some worry in that limited environment of Congress that we potentially focus on the big missions at the expense of the smaller missions, and we've got to find that right balance. Maybe if you want to expand on your comments and the importance of some of the smaller missions.
Yeah, thank you very much. Indeed, I think this is well recognized at NASA, and I've heard Jim Green talk about a cadence, a process for deep exploration in space that you might fly by, you might orbit, you might land, and then you might rove. And indeed, you wouldn't spend all the money that you would have to spend to do a flagship mission on a body that we know little about. And so the smaller missions form a framework, and they set the stage for the kinds of bigger expeditions that we want to do. And as my colleagues here have mentioned, every time we do something in space, it surprises us. And so we must try these smaller missions to find out where the biggest surprises are, and then put our money on making the big discoveries.
Dr. Green, do you want to expand on the importance of the smaller missions?
Indeed, the smaller missions are really our pioneers. They do go out and do some initial exploration. You know, smaller missions in the discovery framework is really the heart of that exploration process. I mentioned several of them in my testimony, like Dawn. Others that have come and gone while I've been at NASA headquarters include Messenger, another wonderful mission. Grail went to the moon, Messenger went to Mercury, and Grail studied the moon in new and unique ways. And so indeed, the discovery line is really quite important for us. And then the next line is New Frontiers. This is where we can now concentrate on the next level of detail, so important for us to make decisions on what our next flagships would be.
Great. Switching now to Mars and, you know, our telecommunications infrastructure in Mars. My understanding right now is that the Mars Reconnaissance Orbiter handles the majority of our telecommunications relay for Curiosity rover, but the MRO was launched 12 years ago. As we look at Mars Rover 2020, you know, I guess Dr. Green or Dr. Farley, would you like to kind of comment on, you know, will we still be relying on the MRO to relay that information back, or are we thinking about, you know, what next steps for telecommunications?
Well, telecommunications for any surface assets indeed go through our orbiters. And right now we have a wonderful network, including MRO is Mars Odyssey. And also, with partnership from ESA, other missions that are also orbiting Mars have that telecommunication capability. So in addition to those two, we also have, with ESA, the Mars Express mission, and now the newly inserted into orbit, the Trace Gas Orbiter from ESA. Now, we also have MAVEN, which is not a prime telecommunication capability, but may become more dependent on using MAVEN as our aging assets occur. So indeed, supporting telecommunications is a real critical element of allowing us to now, when Mars 2020 gets down on the ground, be able to relay that data back. So we take careful operations of all those missions and partner with other agencies.
Great. I don't know, Dr. Farley, do you want to expand or?
Yeah, I'll just say Mars 2020 has a very large demand to downlink data. We have a huge number of cameras. It's quite extraordinary. There's more than 20 cameras on the rover. And we will need downlink. As you point out, MRO is an aging asset. But as Dr. Green pointed out, there are contingency plans to get us the data volume we need.
Great, thank you. And I'll go back.
You bet. Thank you. Good questions. Now recognize the gentleman from California, Mr. Rohrbacher.
Thank you very much, Mr. Chairman. It was noted earlier that one of the purposes of, or one of the benefits, I should say, of your activities is that, well, you have these robots all over the universe and beyond, that you are inspiring people with our capabilities. And Mr. Chairman, let's just note that I've been around for a while, and I think that when we were deciding about the shuttle and we were deciding about space station, a lot of the times the discussion was only on the immediate scientific payback. But I believe those two space projects have inspired generations of Americans now, and that who knows how much more productive our people are, how much more visionary they are because of these investments in the shuttle and the space station, which were very expensive projects, I might add. And back to expensive projects, let me just note that one thing that I find, one of our witnesses mentioned that the Keitel survey was supposed to prioritize, and it just seems to me, standing back and listening to everything, that we haven't had that prioritization. And maybe we should have, there's been, when you have so many projects at one time, it indicates that there hasn't been a real fighting it out of what priorities we need. And I'm not, certainly not an expert enough to tell you what those priorities should be. Let me ask some specific concepts or ideas about the engineering that I don't know about. What type, well, first of all, is there any one of these missions that planned to, we know we've landed the robots on Mars, do we plan to actually bring some material from Mars back to Earth before we plan to send human beings there and bring them back?
Indeed, the Mars 2020 mission, which is going to core rock, providing a detailed look at the past Mars, the geological records in that rock. We are currently looking at a variety of architectures.
Right. But are we going to bring them back?
Our intention would be indeed that as the importance of these samples are noted based on the analysis that we do in situ, that indeed we would plan on bringing samples back from Mars.
Okay. The reason I ask that is it seems to me that rather silly to think that if we can't bring back rocks, that we're going to bring back people. And certainly if we aren't comfortable with the idea that we can bring back rocks, we should be focusing on getting that done before we talk about bringing people back. What type of, the exploration is, to me, that's the most inspiring. I'll just have to tell you that when we talk about going out and visiting those places where nobody has been, and what type of fuel are we using? There was a mention about one of the things when we run out of fuel, it's going to land into Europa or something like that. What type of fuel is now being used in these various projects? We know that you have to have a big rocket to get them going, but if they're going to keep going and through the universe, what fuel do they use?
Yeah, Mars 2020, while it's on the surface, will use a short-lived plutonium isotope, so it's a nuclear power source.
Any other?
May I add to that? During cruise and while orbiting Psyche, our spacecraft will use solar electric propulsion. And this, to me, is so, it's in our heart, it's space age. You see the little blue plumes of the ions being shot out the back, and it's all run by solar power. And in fact, this is another good proof of this technology, which is eventually going to be critical for getting people to Mars.
Yeah, I noticed that I remember the solar sail project, and which also is very exciting. These new concepts that, and let me just note, Mr. Chairman, that the fact that we can actually provide a fuel for something that far away and indicates that maybe we have some knowledge that's going to really help us here. But one last thought, I would hope that, again, I think the moon is close by, and whatever we can actually get a benefit out of going back there, we should. Before you take the next step. However, the most important thing was if Mars, can I ask permission for 1 minute for this question? And that is, you have indicated that Mars was totally different thousands of years ago. Is it possible that there was a civilization on Mars thousands of years ago?
So the evidence is that Mars was different billions of years ago, not thousands of years ago.
Well, yes.
There is no evidence that I'm aware of that.
Would you rule that out? That, see, there's some people. Well, anyway.
I would say that is extremely unlikely.
Okay. Well, thank you all. Thank you, Mr. President. Thanks for the good job you're doing. God bless.
Thank you, Mr. Rohrbacher. Looking forward to finding out what's up there, that's for sure. Just last month, we had a great hearing in here on interspace propulsion, which was super, super interesting. Okay, and now I'll recognize the gentleman from Colorado, Mr. Ed Perlmutter.
Thanks, Dr. Babin, and good morning, and thank you for your testimony today. And, you know, a truism in life is everything's relative. And when we're talking about small, medium, and flagship projects that you all are undertaking, you know, to Mrs. McGillicuddy from Lakewood, Colorado, they're all major undertakings. And Dr. McKinnon and Dr. Elkins-Tanton, I mean, we're here for I dipped into the future far as human eyes could see, saw the vision of the world and all the wonder that would be. And all of you are working on kind of the ultimate question of humanity is why are we here and what else is out there? And so I just appreciate your willingness to take on kind of the nuts and bolts for us to start knowing the unknown. And this committee is so exciting to all of us up here, and to hear the work you're doing, we appreciate it. Now, I'd like to start with Dr. Farley. One of the things that I am focused on is trying to get our astronauts to Mars by, you get it, guessed it, 2033, all right? And so, first question I have is for you, how will this rover, you know, 2020, our mission in 2020, how will that help us, inform us to get humans to Mars by 2033?
Well, I think it's important to note that Mars 2020 has a very strong collaborative involvement from the human side of NASA, and that is manifested in several different ways. Most notably, you heard about the MOXIE demonstration of in situ resource utilization. In addition, we have a weather station which will characterize the environment, will also characterize dust, and dust on Mars is a big concern for human explorers. And in addition, during entry, descent, and landing, we'll have a very sophisticated observation package. Understanding what goes on during EDL is absolutely critical and almost impossible to simulate either on a computer or in an analog experiment on Earth, so this is very important data. And as Dr. Green mentioned in answer to the question of bringing rocks back before people back, it's a very sensible thing to do. Obviously, there's no commitment to do that, but there will be a tempting target to learn from if those samples come back.
Okay. Dr. Elkins-Tanton, where the heck is Psyche? I mean, other than up here or wherever it might be.
Psyche is in the outer main asteroid belt between Mars and Jupiter. It's about 3 times farther from the sun than the Earth is.
Okay. Dr. Pappalardo, my question to you, often I talk about Star Trek or Star Wars or Men in Black, but what you're doing reminds me of 2001: A Space Odyssey, and, our mission at that point to get to Jupiter. So explain to me, in this investigation study of Europa, what do you see already, and what do you expect to see from this mission?
Sure. Let me preface by saying I'm a big Trekkie, influenced the fact that I'm here. And our Europa science team of about 130 people, we have as our mascot, our totem, a giant monolith that we tote around to our meetings. Actually, we have 3 now. So we have tantalizing hints from the Galileo mission about what Europa is like. At high resolution, we have precious little data. We have 1 6-meter per pixel image. We have 10-meter per pixel images that you can count on your hands and toes to get an idea of what Europa is like. And so this creates this picture of what we think it's like. Ice shell probably about 20 kilometers thick above saltwater ocean, and then the rocky mantle below. But right now it's kind of a uniform picture, whereas any world you explore in more detail, and then you find out how it varies from place to place. We've seen this happen with our understanding of Mars, where we first thought it was a cratered ball because we saw the cratered part of it, and then we started understanding more and more, and now it's at the outcrop scale we see differences. So we're going to understand how Europa works as a world. We're kind of in our level of understanding that we were before plate tectonics on Earth, where we don't really get how all the little pieces we see at the global scale fit together, and we're going to find more little pieces as we explore with the Europa Clipper.
Thank you.
If I
Thank
could-
you, Mr. Chair, and I yield back.
I'll just pipe in just
I'm
for a
sorry.
second. We have tantalizing evidence from the Hubble Space Telescope that Europa is venting material into space, and we hope when we get there we'll be able to confirm that and literally fly through it and sample it and analyze it.
Thank you, Doctor.
Thank you. Good questions and great answers. Now recognize the gentleman from Oklahoma, Mr. Lucas.
Thank you, Mr. Chairman. And I share my colleagues' enthusiasm up here and clearly the enthusiasm of the panel. Let's visit mechanically for a moment about Dr. Farley, about the nature of the Rover programs. A lot of the citizens back home very sensitive about how we spend our money. Could you take me through a discussion about Mars Rover 2020, the advances in the technology and the science gathering used in that compared, say, to Curiosity? As I explain to my constituents back home why it's important we do this.
Okay, well, in reference to Curiosity, the reason this mission can be done in a cost-constrained way is to take advantage of the platform that the Mars Science Laboratory developed. It should not be underestimated how difficult any new undertaking in space is. So we start off with that, and this allows us to actually focus on the stuff that is new. And there are new science instruments that will make new kinds of observations. And I think those they will be directed towards characterizing samples that will form the basis of a discussion as to whether those samples should be brought back. And if those samples are brought back, I think they will revolutionize our understanding of many different things. If you look at the history of our understanding of many aspects of the solar system, it was completely changed by the return of the lunar samples. And that, of course, is an abiological world. My expectation is if samples come back from Mars, this will be a revolution that goes way beyond sort of planetary science and geology. It will actually extend into asking and looking at samples for the first time to address questions about what life, not as we know it, might look like. And I'll just put it out there as a profound question for which we don't have an answer. How does one look for life as we don't know it? And we may have samples in our collection in 20-some years where we will need to answer that question. I think the public will be fascinated by that question.
Dr. Pappalardo, discussing the plumes just a moment ago, tell us mechanically about what will be involved in being able to use the clipper in a way to verify their existence, whether it's navigating the flybys or the sensors on board. Expand for just a moment on that, if you would.
Well, first, there are continuing observations with the Hubble Space Telescope, so we expect to have new data before we arrive, so we can understand if they're real, if they're periodic in some way. But say we don't, or say they're sporadic and we need to understand them better. We would use the time, we have a big looping first orbit. We would use that time to monitor and try to understand whether there is evidence of plumes, both from imaging and from ultraviolet observations, where we could see the glow from such plumes. And then during the mission, we're planning on monitoring the whole time when we're a little farther from Europa to look for plumes. And then if there are plumes, then we will certainly want to target them, whether it be in the primary mission or the extended mission. We'll figure that out. But we'll want to fly through as low as possible, meaning about 25 kilometers, 16 miles off the deck, if we can, depending on the location. It'll depend on whether we can or not. And for that matter, how much particulates, because you can't risk the spacecraft. And by flying through, we'd be able to sample that stuff directly and get a direct sampling of what's in the interior of Europa. We don't know for sure. Assuming plumes are real, we don't know for sure if they're coming from the ocean or from lakes within the ice shell, and we would analyze the gas and the dust that's coming up to say a lot about what the interior composition of Europa is like. This is analogous to what Cassini has done at Enceladus at Saturn, which does have plumes that spew into space.
So an incredible amount of prep, an incredible amount of skill in moving the mission, and just a little bit of luck would be a good thing too.
And we have a group of scientists, we're thinking that through as we meet and discuss the possibilities and working with the engineers to do so.
Absolutely. Thank you, Doctor. You're back, Mr. Chairman.
Thank you. And now I recognize the gentleman from Virginia, Mr. Byer.
Dr. Babin, thank you very much, and thanks all of you for being here. Dr. Farley, a relative softball question, but in your testimony, you say that past life, Mars 2020, seek evidence of past life in a fossil-like Earth-like environment that existed in the first billion years after the dawn of the solar system as, quote, some of the most profound scientific questions of our time. Why are they profound?
Well, the two questions that I was alluding to there are is there life beyond Earth? And I will just make the general observation from my interaction in the science community. The discovery of thousands of extrasolar planets has converted this question from something where most scientists that I knew would say, it doesn't seem that likely, to, wow, it seems really unlikely that we are alone. The only way I think you could really put some scientific evidence to that is if you look in a habitable place, is it inhabited? There may be lots and lots of habitable places out there, and that goes to the question of the spark that makes life happen. And so that, I think, is a really profound question that we will go after. Is life out there? Was it out there? And what is necessary? What are the environments like where life might evolve? And those two are really profound questions.
Great. Thank you very much. Moving from life to metal, Dr. Elkins-Tanton, a couple of quick questions. How do we know that it's metal? Is it a spectrometer or whatever? How do you know it's the only one in the solar system? Why did you name it Psyche? And do you really think it used to be a planet and the rock and the like was stripped off of it? That it was like Earth or Mars or Venus. So.
Right. Okay, let's see if I can remember this and get it all in your time. So the first question is, how do we know it's metal? We've never seen Psyche visually as more than a dot of light, but we get radar returns from Arecibo, which seems to me to be also just a technological miracle. We can actually send radar from Arecibo, get the returns, see that the radar has interacted with the material of Psyche in a way that it only interacts with metal. So that's a really key one. We can also see its reflected spectra consistent with metal and its density consistent with metal, but the radar returns are the key. Okay. So we're pretty certain it's metal. There are other smaller metal asteroids like Cleopatra, which is shaped like a dog bone. If you haven't seen it, you should Google it. It's a great one. But they're all much smaller. They seem to be the shrapnel of leftover from planetary collisions. All the really heavy, rocky, metallic material is either in the inner solar system or in the asteroid belt or hidden inside ices and gases in the outer solar system. So we're pretty sure that what we see in the asteroid belt is it for metal, and Psyche's the only big round one. Now, Psyche was discovered in, I believe, 1852 maybe, I might have the date wrong, by an astronomer in Naples, and he named it Psyche. It was the 16th body found in the asteroid belt by a group of astronomers called the Celestial Police, Die Himmelspolizei, who were trying to set right to the solar system and find the planet that was there, and they didn't, and they were naming them all after gods and goddesses, and so Psyche's number came, and there it is, Psyche. There was one more question. What was it?
Did it used to be a planet?
Oh, we're pretty sure it was, but true to my scientific training, everywhere I've been in the world and given talks on Psyche, I've asked scientists, what else could it possibly be? If it's not the core of a planet, how do we make this? And our best other guess is that it could be material that was had all the oxygen stripped off it by heat very close to the young sun. Theoretically, people think that kind of material could exist, but we've never found an example of it. And so if it's not a core, that would actually be more exciting. It would be something we've never seen before.
Exciting either way.
Thank you.
Pretty cool, yeah.
I think so.
And I want to point out that Jules Verne did think we could do a journey to the center of the Earth.
I visited that Icelandic volcano. It didn't work for me.
All right.
But, yeah.
And Dr. Green, you talked about looking for evidence of organic materials on Ceres, and that on Bennu, I hope I pronounced it right, is believed to contain water and organic compounds such as amino acids. Have we gone beyond amino acids to proteins, to nucleic acids? We're going to leap to DNA and RNA.
Well, of course, we would call that a ever-increasing knowledge about potentially the right stuff that life either is made of or produces as a byproduct. That's all part of what would be a ladder of life. But the only way we can definitively determine what's really at Bennu is to bring samples back, and that indeed is planned. When we get into orbit around Bennu, as we start getting in August of next year, we'll be studying it for about 500 or so days, picking the right location, going down, sucking up material, perhaps as much as 1 kilogram, and then bringing that material back. And that's when we'll do the detailed look at what's in it. It'd be great to find more complex amino acids and other organics. I'd love to.
Thank you, Mr. Byer. Now recognize the gentleman from Florida, Dr. Dunn.
Thank you very much, Mr. Chairman. I think, the Space Committee always seems to be the most inherently optimistic committee of the House, and, the can-do attitude of our panelists is absolutely infectious. I can only hope that you'll expose yourselves to the Senate sometime soon. I want to frame my questions to the panel with this thought. The proof of life that is truly extraterrestrial life is an event that is on the level with the first moon landing. So long after posterity's forgotten all of the proceedings of this committee and relegated the history of our planetary explorations to the dusty bookshelves, everyone will remember the event that proved extraterrestrial life. So with that thought, Dr. Farley, let's say everything works out perfectly on the Mars 2020 lander. You obtain appropriate terrestrial samples. What would you consider to be the elements of a biosignature, a biotic chemistry, if you will?
So I'd give two different answers to that. One is, what can we detect with the rover, and what could we detect if we bring samples back? And with the rover, we have the capability to make a map at the scale of about a postage stamp of the distribution of organic matter. That's one of our key observational capabilities, to take a rock and make a map of organic matter. And on that same postage stamp size piece of material, we can also map the elemental composition. And when one looks at ancient terrestrial rocks, this co-registration of organic matter and elemental composition is the key to identifying, on a planet where you already know there's life, to identify the most ancient life on Earth. So we will make those kinds of observations, but just like with the terrestrial case, those kinds of observations are seldom definitive. They're the kind of thing people argue about for decades. And if we bring samples back, there are a far greater diversity of observations we can make. Dr. Green was talking about making observations of the ladder of life, looking for more and more complex organic molecules whose composition is only reasonably associated with life as opposed to abiological processes.
I guess I kind of thought that the problem with bringing it back is everybody always wonders about contamination, and, you know, did you sterilize the ship so thoroughly on the way out and the way back that you can be certain that this came from Mars?
Yeah.
And, you know, so if you're doing the test as they did on the Vikings, you know, they are in situ on Mars, and if you could design a better test, a better chemical test, what would that be, and would it involve, as you and I spoke before the meeting, stereoisomers and?
So one of the complications of looking for ancient life is that there will be degradation of organic molecules.
You're still looking for ancient life. I'm looking for life today.
Right, right. We have no capability on the rover to look for extant life at the microbial scale. We can't tell the difference between live and dead. But if those samples came back, as I mentioned before, I think there will be a lot of interest in actually developing technologies. And they would include things like stereochemistry and that sort of thing.
So would you elaborate, because I'm not sure everybody on the committee is thinking about stereochemistry, what's the significance of discovering an ongoing biochemical or chemical process, a biotic process, that has, you know, a solely left or right-handed metabolite?
Sure. So one of the key ways that one identifies molecules that are involved in life is that all life has a preference for a particular handedness of one of the organic molecules. There's two different conformations that these organic molecules could be in, and most abiological processes produce them in equal abundance, whereas life, because it has a machinery involved, very specific machinery, tends to produce a specific chirality, a specific conformation of these organic molecules. So this is really a critical observation for establishing that life is involved. There are very, very few abiological processes that would produce stereochemically specific molecules.
So the production of a stereo-specific metabolite would be a pretty strong presumptive proof of life, extant life, on Mars if you ran it the way the Vikings rover ran that. What the Viking rover did is run that test without stereoisomers.
Right, right.
So
Yes.
if you ran the same test and checked for stereoisomers by having left or right-handed substrates.
Yes, that would be a very important test, and I'm aware that there are instruments under development for actually making those kind of measurements in space.
I agree there are. I'm out of time. I would say that that's about a 2-kilogram package. I look forward to talking to you outside of the committee structure, and I yield back.
Thank you. You remember a lot from your training, you know, Dr. Dunn. Let's see, another gentleman from Florida, Mr. Posey.
Thank you, Mr. Chairman. Dr. Green, traditionally planetary exploration was a public sector endeavor that taxpayers took care of. Today, the U.S. private sector companies are beginning to invest and develop planetary exploration programs. What is NASA doing to facilitate and encourage private sector investment and participation in planetary exploration?
I believe there's a whole range of things that we've been involved in. If you take an example of the concept of going to asteroids and being able to extract certain metals and other compounds of interest, the first thing that they're going to need to know is where are they? What is their characteristics? How to get to them? And indeed, we are doing an extensive finding project where we'll find our small bodies. We'll catalog and characterize them, and all that information will be critical. And we've discussed that openly in many different meetings working with that sector. Another sector is a series of commercial opportunities going to the moon. Now, this could be a really important element for scientists to be able to work with the commercial entities and be able to obtain rides to be able to bring back material or examine certain regions on the moon that are extremely important. The moon is still quite valuable in terms of being able to provide us an enormous amount of science that can be done. It's been a witness plate of over 4 billion years of impacts, can tell us a lot about what's happened to our environment and what's happened to the Earth. So those partnerships are beginning. There are some that are done with through a Space Act agreement, and others are done through collaborations and discussions at a variety of venues.
Thank you very much. That's a good answer. Given the important role of robotic planetary missions in advancing human exploration capabilities, how can the current and future planetary missions be integrated in the human exploration roadmap, which we've asked NASA to produce?
Well, of course, from my perspective, planetary scientists are really the guides. They're really the ones that go out first. Human exploration is not Star Trek. It's not go where no human has gone before. And our program in NASA is really all about sending humans to locations beyond low Earth orbit, out into the solar system, be able to live, work, but also return. And all those require not only where you're going, but the characteristics of how to get there, what are the kind of science and other activities one can do on station, and then, of course, the challenges of entry, descent, and landing for any of the bodies they choose to go to. We pioneer a lot of that, in terms of being able to look at those environments, collect that information, but also pioneer some of the initial technologies that allow us to get our rovers and other machinery at various locations, whether it's the moon or Mars.
Okay. Can you describe the infrastructure that missions will be putting in place around Mars and Europa to support future missions? For example, will NASA be able to use the Europa Clipper to support future Europa missions, namely the lander?
Yeah, actually, as Lindy mentioned earlier, in planetary science, we really have a very important paradigm that we follow. It's flyby, orbit, land, rove, but also return those samples. And indeed, the Europa Clipper gives us that opportunity to do a detailed examination of Europa that provides high-resolution imaging that gets us right to where we want to go, that makes the next mission, which would be notionally a lander, to be able to land safely and perform the science that we want it to do. So indeed, each of these missions are very much related and depend on the success of the previous mission.
Thank you very much. I yield back, Mr. Chairman.
Yes, sir. Thank you, Mr. Posey. And another gentleman from Florida, Mr. Webster.
Thank you, Mr. Chairman. Dr. Green, is there any interest in going to the outer planets to do the same level of investigation and so forth, or is that just too expensive and too far?
Well, indeed, when one looks at the science that's been well delineated by the community and the National Academy's Planetary Decadal, we have an extensive desire to be able to go out to the outer reaches of our solar system where our planets like Neptune and Uranus reside. Neptune and Uranus, although they are big, what look like giant planets like Saturn and Jupiter, they actually are very different in many ways. They have a whole series of different compositions associated with them. We call them the ice giants. They're not completely hydrogen and helium. They have ammonias, and a whole series of other elements that they have obtained in that accretion process that we know very little about. And so being able to go out to Uranus and Neptune are extremely important. We've just completed a major study and have worked with the scientific community to determine what are the characteristics of the measurements we want to make in those regions, but also how are we able to get out there perhaps in the second half of the next decade and really get into orbit and analyze that environment.
Is that desire, which you spoke of, funded?
Right now, that's only at the study level. The planetary decadal is quite clear that the top things that we should be doing, we are doing, but you know, you have to prepare. You have to spend some time on your future or you don't have that future. And so while we do this planning, while we do this mission concepts and studies, those are indeed laying the groundwork for our future work.
Is Voyager still broadcasting?
Yes, both Voyagers are still broadcasting. Now, they're very far away. They're more than 120 astronomical units away, where one astronomical unit is the distance between the sun and the Earth. So they're very far out there, and therefore, and they have little power left, although it's a radioisotope power, it's a long-lasting power system. They're sending back a handful of bits whenever we can turn our big telescopes and bring that data back. But they're doing a marvelous job really exploring that outer reaches of the heliosphere, we call it.
What's their wattage?
I would only guess, but I would believe it's on the order of tens of watts. That's all that's left on it.
And then what would be the final date that it won't be able to broadcast anymore? You're saying it's diminishing now, right? Is that what you said?
Yeah, it utilizes radioisotope, plutonium-238, which decays over time. And how that works is you bring a mass of plutonium together, it's radioactive, you shield that, and that radioactive capability where the nucleus of the atom blows apart heats, and that heats a sleeve that's around this material. And then that heat through a thermocouple is used to charge a battery, and then you run your experiments off of it. And so over time, as the radioisotope decays, then there's a little heat involved. And now you have major power management activities that you have to do, which they're doing to really keep the spacecraft going. Because not only is it providing power, but it's also providing warmth for the instruments and the spacecraft subsystems. I can't give you, although I'll take for the record and get back to you on exactly what our prediction is when it will really have not enough power to sustain itself, or it'll be at a distance far enough away that we will not be able to track it.
Thank you very much. Yield back.
I could add just one thing to that the New Horizons spacecraft, which passed by Pluto and is on its way to another body in about a year and a half, will also leave the solar system, and it's also powered by a similar radioisotope heating system. And we anticipate that we'll be able to contact and operate the spacecraft into the 2030s.
Thank you for those fascinating questions. I want to ask one more question. Why do we think that Mars lost its atmosphere billions of years ago, and Mars is farther away from the sun than Earth? And I'm just going to, Dr. Farley, would you take a stab at that?
There may be others here that know more than I do about this, but this was one of the central purposes of the MAVEN mission, to try to understand why the atmosphere was apparently lost. And one of the leading candidates is that the planet loses hydrogen and to space, and that causes, that hydrogen is produced by the breakdown of water, and so you break up the water molecule and the hydrogen escapes. You cannot reform the water molecule, so that's a way to desiccate it. It's by interaction with the solar wind. And one of the key reasons for that is that Mars apparently lost its magnetic field very early in its history, whereas Earth did not. So the magnetic field protects the Earth from the radiation from the sun that causes this to happen.
Good, thank you. Anybody else?
Yeah, I'd love to add to that. I've worked on that directly. And so this is part of our interest in Psyche as a core, is to understand the magnetic field. But to add to what Ken has said, it's also possible, another hypothesis is that when Mars was very young and still hot, its atmosphere would have been inflated through heat to be further away and less well bound to the body itself. And the more active young sun could actually have stripped it at that time. And so we don't know exactly when it was stripped or the processes, and that's another thing we'd like to learn to find out how applicable it is to the Earth.
Great. Those are fascinating answers. Thank you so much. I think I'm the only member left here. But I want to say how much I appreciate all of you fascinating and well-educated scientists for being here, and we appreciate your valuable testimony. And also any members that the record will remain open for 2 weeks for additional comments if any members would like to submit those. So with that, this hearing is adjourned. Thank you.